All right, hello. So yesterday I tried to make this stream, and it took it's supposed to be about 30 minutes, and it wound up being about 4 hours. So mostly because I ran into a bunch of bugs with my toolkit. So hopefully that's fixed, and we can get back to work here. All right, so what you're looking at is the B4 virtual machine, or rather a shell for it. I call it B4. I is the interpreter or interactive assembler, I guess, and X is the extended experience that has all this fun stuff on it. So this down here is a view of memory. This is the terminal that we're working on. So all this is doing, this is another view of memory basically. And the way it works, we can pick a memory address, and I believe this is set to start right here at 140 at the moment. We're going to move that a little bit. Not 140, but I don't know how to say this, but 140 hex. And let me turn this off real quick in 1 second. So if we, say we put the letter C at 140 and we write the byte, that should show up in the upper left-hand corner there, so it does. And if we go down even further, like, X 180, write byte, well, that wound up perfectly even, but how do we say X 210, right? There you go. So now you got stuff on the screen. All that's doing is just writing to memory, and this is a different view of the memory. So you call that a memory mapped, quote unquote, hardware device. Obviously, this is just not hardware, but we're pretending this is a hardware device attached to this virtual machine. So that's the idea, and that's what I want to fill out. So rather than poking directly into memory, I want to create like a little BIOS that gives us something to work with here. So let's see, emacs.plan.org has some of the stuff. So yesterday, like I said, we had a whole bunch of issues, or I had a whole bunch of issues, because this tool just isn't up to speed. I use another version of this system called, I made, there are multiple implementations of the interpreter, the virtual machine and the interpreter and whatnot. This is one of them that runs in Decker, which is an open source tool. It has a little programming language called Lil. It's really, really neat. And I've been prototyping a lot in here, and I kind of got this further ahead than all the other implementations. And so then yesterday I was expecting some of those features to be there, and I just forgot that I hadn't implemented them. And there were some bugs. Anyway, so today, just over the course of the day, I kept feeding Gemini, which is this tool from Google. And I kept feeding it like, hey, fix this bug, or here's a test case. I write like a very short test case for the tests, which just kind of exercise this thing like this bug here. If you have a word where the first two letters are an opcode in V4, it was treating it as the opcode and not calling the function, which is a bug. And so it fixed that. And I would write these little test cases, and then it would go and fix them for me. So it did like a bunch of them. They were all pretty easy fixes. So, but it did save me from doing the work. So it was great. And it's hit or miss. Sometimes it, first of all, it's Pascal. So sometimes it forgets things about how Pascal works, because it's not a very common language. You have to define everything, not twice, but anything that you want public, you have to put in this interface section up here. And sometimes it would like put things in the implementation, which is where the actual code goes, and it would forget to put it up here, and then it couldn't figure out why I couldn't use it, and it would try and like backtrack, and I'd have to stop it and say, hey, no, you did it right, just expose this function or something like that. So it's pretty smart, but it's very it gets discouraged easily by little errors and whatnot. Hang on 1 second. I have a giant grocery list that's blocking my view here, and I'm going to close that. Okay, so there was some stuff I was going to order. So there you go. Some personal history about me, I guess. All right, so I'm just going to jump back in and just continue working with this. So basically what where what I had before in the BIOS. Well, first of all, there is something called the BIOS, but it's like old, and it's actually more like the start on a fourth interpreter. Hang on a second, am I not streaming? Okay, sorry, my chat was saying that it couldn't see my screen. So, but it says I'm live, Open Studio. Okay, so there we go. All right. Oh, another thing I added that I had lying around from ages ago. Actually, the guy that made Redis, his name is, or he goes by Anti-Res online, and he made a tool called Line Noise. And I kind of many years ago I had seen this before he was famous, and I made this thing, which is, well, I'm talking about this line right here. You can't really see it, but if I'm pressing Control P for previous and Control N for next, I'm scrolling through that history. So it remembers my history. And that's pretty neat. So I just plugged that in and after work today. And got it working again and hooked it up to this. And so now we don't have to retype the same words over and over again. But I haven't typed it yet, so I do have to type one thing, which is to assemble. First of all, what directory am I in? I'm in that directory. So relative to that directory, there's BIOS B term.v4a. Unknown word SCRW. Okay. So I couldn't assemble it because I put a bug in there. BIOS. Yeah, I was kind of rearranging the words and changed them a couple times. Discard your edits. Yeah, I'll discard my edits. I don't even want BIOS B4a. I want term.b4a. Okay, now that's a little dark, but that's what we have. Okay. Oh yeah, so I named it back to terminal buffer, terminal width, terminal height, and so this should be trm h and trm width, terminal height, and actually I don't even need this right now. So this should now be terminal read from the terminal width, read the terminal height, multiply them together, and that's the number of cells that are on the screen. This syntax didn't work yesterday, but it should work today. That was one of the bugs that got fixed. And then we're going to divide by 4. So I could have just said C4 div rather than shifting and all that stuff. To get number of ints. And then we're going to I'm not sure what that was for. You should just call it directly. I think I was trying to make I don't know. I was in the middle of editing something and save this file. All right, so that's how the code should look. And I think we decided we were indenting 3 spaces in this language. So I'm indenting 2 here. But they're almost all 2 spaces, so it looks weird if you don't indent 3. And we'll put it right here, just kind of line that up a little bit. All right, so basically, let me read what this is. So you kind of got that. So this is loading an integer, so clear screen, right? Load an integer, and the integer is composed of 4 bytes, and these are quoted spaces. And then it's going to fetch the terminal width from this cell right here. So the cell is 4 bytes, this address. Fetch the terminal height from this address. And this marks, oops. This marks it marks the label or whatnot. And put that right back. The name of this machine is Strong Bad, but it says Mentok at the top. 2 different cartoon characters. Okay, so anyway, so multiply those together. That's the number of characters we need to fill in. Divide that by 4 to get the number of ints, as it says. And then we're going to call this function fill memory and return. I might call this mfill. Like I'm not entirely like film. It keeps looking like film to me, so I'm gonna call it mfill. Fill memory, yeah, or memory fill, whatever. Okay, so that's the idea. So hopefully now this will, now that I fixed it, I actually broke the thing. So yeah, I can press Control P to get that. I don't have arrows working yet. TRMW, because it's just TMW and TMH. Okay. Oh, and the thing that I was trying to quote there was the screen. So then, which I didn't talk about. So fill memory. It takes 3 arguments. This is like the before and after picture. So on the stack. So this is a stack machine. It's got stack. So 1, 2, 3, and you see they're on the stack here. If I say swap, they get swapped over there. If I zap the top thing, whatever. So zapping them that's the word. Okay. Dropping them, I guess, but would have been another nice way to say it. And what we're going to do here is we have to call this, or we have to populate the address of the terminal buffer, which is again reading this. So this is where this is where the terminal resides in memory. It's at that 0140, which in little endian would be 000140. All right, so that's it. The @ sign is an assembler macro that says, load this address, and so it lays out an operation like this: li to load an integer. The integer is the address of this wherever it winds up being assembled to, and then the @ sign tells it to read it replaces it with a, so it's basically like li some numbers, and then read integer, and that's what @ does. So that's what all 3 of these are doing. They're reading these numbers, putting those numbers on the stack. They're reading the 40, which is 64, and 10, which is 16. So it's a 64 by 16 grid here, and that's the memory buffer. Okay, so hopefully this will work now. I think it worked. Okay, and so now this is the assembled code. It looks a little weird, but you can see there's an @a DC, bang a, and then the .f turn is actually a macro. It does something other than assemble directly to a thing. It actually doesn't leave anything here, but it remembers this position so that we can jump back to it later. This is a for loop. So, but basically, @a is a register, or a is a register. And if we see what's @a, whoops. It's not supposed to break the terminal there. I should trap that error, basically. So there's nothing in that register right now. I think we hit like that. I would say $R, we can see what all the registers contain. But you can't see all of them because the screen is too small, which I will have to deal with soon. But you see there's nothing in there. And if we say, some numbers like AABBCC, whoops, AABBCC 11, and then we say R put, or actually put into R, Then we can look at the registers again, and you'll see that R has that number in there. So all the letters, there's a register for each letter, and then some extra ones like these down here, based on the ASCII table. And so this says whatever that's there, stick it onto this other stack, move it from the data stack to the control stack. So you have this number, move it to the control stack. At first it puts it on the data stack, and then DC moves it to the control stack. So now it's on the top of the control stack, and we can move it back with CD, and do whatever we want with it. Anyway, so the pattern of at A move to the DC, data, and then later at the end CD, and then put it back in A. That's like a restore register. So we can do whatever we want with that register, and then get the old value back, and we haven't disturbed anything. And we can use it as a local variable. And then what we're going to do with it is loop this many times, whatever so the address goes into A, right? So first we back up whatever A was, stick it on the control stack. Then this bang A puts the whatever is on top of the stack into A, and then we do a loop. So that is our control variable. So we're saying number of times. I'm sorry, actually, hang on. A is the register of the address that we're writing to, and then the next thing on the stack is the number of times that we're working on, and that's what this for loop does. And with that loop, inside the loop, we're going to duplicate that thing. So whenever something's on the stack, so we have a 0 there. I put a 3 here, and we duplicate it. Now we have 2 3s, 3 3s, and so on. So we're going to duplicate it, and so we make a copy. I'm sorry. The .f actually moves that to the control stack, and then there's this operation next, which is down here, which checks that number. And what it does is it checks the top number on the control stack, and if it's 0, then it moves forward. So that's the end of the loop. And if it's not 0, it moves back over here. So it jumps back a certain number of things. This hx is actually a negative number. There happens to be an opcode that's called hx that. Otherwise, it would say like F4 or something like that. It's some like negative number of bytes to jump backwards. Anyway, the point of this is to fill memory. So we're looping through, and then every time what we're going to do, finally, the last thing on the stack after we've moved A, the address into A, the loop counter into the control stack, and that leaves this I, which is the integer. I should call it pattern, I guess. Maybe P would be a better name. To pattern P. How about X? X is the pattern. Oops. Yeah. So we're going to copy that pattern over and over again as an integer. So we're doing 4 at a time. I guess maybe I could have done it with bytes and done 1 at a time, but whatever. Okay, so hopefully that will clear the screen. So now that I've loaded it, we can see that it's actually defined. We can also see that my screen is needs to be adjusted a little bit like that. Let's do that. There we go. And now we can see that these things are defined. And what we want to do is we're going to call this clear screen. And what it should do is loop through. Basically, what I was saying is it's going to copy. So this plus A takes whatever's in A right now, adds the number to it, which is a constant 4, C4, and then leaves the old value of A on the stack, and then write integer takes that value and says, okay, that's the address I'm going to write to. So that address keeps moving by 4 every time, and that's how we get it to do a for loop. And then at the very end, we pop the pattern, restore the A register, and return. So that's clear screen. And when I do that, you're going to see a bunch of these @ signs here, because that's what a space looks like in as an opcode here. Like the number, 20 in hex is the number 32, which is the space character. But as an opcode, it's @@, which reads whatever's in the @ register. Clear screen, which is like the first register, 0. Okay. So that didn't do anything up here, but that's okay. If we go back and we say like 150, we'll do like 158. I don't know what that's going to look like. I guess we have to put like a variable. 158, write byte. There we go. So there's that letter. And then if we write clear screen again, it goes away. There you go. Okay. So that's what I have so far. That's clear screen. That's the start of this terminal system. So the next thing I want to do is on my list, and I don't know exactly what it is, but let's take a look. Okay, so we have the terminal buffer, that's the pointer. We have the width and the height, which are just numbers that we've hard-coded in RAM. We can adjust them, but for now they're default values. We have clear to screen. All right, so now I want to do what I just did. I want to find a cursor position. So I'm going to add another number here called cur. And I guess by default it should just be a 0, 0. Yeah, that's fine. Did I do that right? Let me think. If I write it 1600, we have 0. We have, let's say 55332211. Let's do 6677. 44556677. Those are all ASCII characters. So this is another way to put. This is actually assembling these bytes directly into that spot. There we go. And then if I say once, yeah, I would just read that as an integer, and then on the stack they're reversed. So the lowest bytes are the first one. So I do have it right. Yeah, the lowest byte is first, and then this is the other one. So I'm treating this as two 16-bit values, I guess, even though they're. Should I do that? Maybe I should just one 16-bit value, because you're not going to have a 256 line screen or a 256. Like however big you make it, it's not going to be. So cursor position. X and Y. Yeah, so 8 bits each X and Y. Okay, so that's the cursor position. So let's, I think we can clear memory, right? We can completely reset everything. Yeah. And then load it again. So I'm going to put it like this. So that way we can run it over and over again. Can I put it all on one line, see screen? Yeah, I can. Okay. That's clear screen. Now if we say at cur, we should get just a 0. Yeah. I'm going to put it actually in the middle of the screen now. Let's put it at 16 and 4. Oh. What happened there? Not sure what happened here. Okay, so we have this number 410. So I want to extract them and get the so we have the cursor position. That's just a variable. But let's break that into the current x and the current y, or the cursor x, current x, current y, cursor x, cursor y. So to get those cur x and cur y, those are functions, so we're going to return something. And they're going to fetch this variable, so fetch the cursor. And I can already see that I'm going to run out of space here. Because, like, you can see, wait, what? Oh, I already have, right? Because if I write like H-E-L-L-O, yeah, you can see it just started to write them and I ran out of space. So I have to move this down. So let's move the, we're going to move it to just like address 400, which is like 1024 in decimal. All right, so now if I load it, you can start to see, you can see H-E-L-L-O. I don't know if you can see, but H-E-L-L-O. Of course, those don't mean anything, but you can put whatever data you want. It's never going to get run because there's a return statement in front of it. So unless you jump right to there, you can put any data you want in there, which is kind of what we're doing. We're allocating some space to put the screen buffer in there. So that, the screen buffer could be right here if we wanted it to. But I'm going to put it just kind of further down in memory. All right, so clear it, load it up again. All right, so I got rid of the hello. So you see these RI returns. That's loading this value right here. No, it's this value right here. This is the address of cur. So if I say, if I quote that, you see we have 11A. So what's A in decimal? 1A in decimal would be 16 plus 10 is 26, right? Which is the number, the 26th letter of the alphabet is Z. And then there's a 0th item, which is the @ sign. So 11A would be the ASCII code for that is register Z. Okay, so basically, and that's why we have ZA, right? Is that right? No, sorry, 1A is Z, is 26, so that's the Z, and then the other one is the A, right? 1 is A, so Z is 26. And so those two numbers are these 4 bytes, and that's where the cursor is, right? That's where the word, the label cursor is. So this value right here, it got assembled to that address in memory, 11A. So if we look at 1, 1, and we go to A, 11A, we see Control P, Control D. I need to have a toggle on here so you can switch these to like hex or ASCII characters or whatever. Because right now it's only showing the opcode, and like it's hard to do the. Like you might want to see them as numbers or whatever. But anyway, that's these two numbers right here. So if you see PD here, and we switch this to like 11, that should change to Q, right? We would think that would change to Q. So watch right here when I press enter. Yeah, Q. Right. So clearly that is the address of the cursor. It is loading that, so it says load integer, and then loading, so as this thing is running, right? So this is a function. So we're going to jump here to wherever it starts, which is right here. And it's going to load this integer, which is the next 4 bytes. Oops. And then once it's done, it's going to read something out of that address. And that is reading the current value of the cursor, putting it on the stack. So when we run it, we say cur x, we have 410, and cur y, 410, which is the same thing as if you say at cur. Obviously, we don't want them all to be the same. We're gonna do something about this. Okay, so what do we want to do? Well, we want to split that number. And so which one do I want to be the x and which is the y? So the 1, 0 is the lowest one. I think that's going to be the x. So I think we're gonna make that the x. And so the low bits are the x, and so we're going to say 410. So 410 low is what I want to say. Low doesn't exist yet, so let's make it. Pascal had this high and low, like you could set to one. So low is just going to be, we're going to load the byte FF, which is 255, which is all 8 bits are set to 1, and we're going to AND it and return. So if I do that again, so I say 410 low now, we should get 10, right? And if I say FFCC low, we should get CC, right? Okay, and then so now we want high. And we can just do that, except we want to shift it the other way. So we could say div 4 or div 256. Is that right? Oh, so yeah, this one an 8. So div 256 div. So how do you do that? You would say my I'm trying to think like the way to do it that's slower than this or faster than this. So I think we want to shift it right 8 bits. So C0, C8. There's no C8. I think the fastest way to get 256 on the stack would be load by FF, duplicate it, constant 1 add, it's called stack juggling. You have to juggle this in your. So you have a stack. You can only work with the top item or top 2 items on the stack, right? So what's on the stack right now? Originally, you have the number. You have like a n, and then right. Return high second byte of int n. Of 60 of high, so basically bits 8 through 15 of n. right, so n is on the stack, and then we're going to return, you know, some value. All right, so n is on the stack, and then what we want to do is we eventually want to say, you know, n shift right 8, or divide by 256, n div 256, and then so that shifts the bits over, and then we want to say ff and to wipe out any other bits that were there, and then return. Actually, we could just call low there. In fact, if you want to be super evil, you could put high first and then let it fall right through. Right? Oh, that's the kind of thing that is dangerous with fourth or with fourth-like languages. We can just let it fall right through. All right, so let's just do so you know, you can load that integer by saying load 01, right, which would be 0000. All right, so that took 5 bytes to put that on the stack. Now I'm trying to golf it a little bit. I want to shift left right 8. So there's no constant 8, and maybe there should be. Maybe I should go all the way up to 8. I have constant 0, 1, 2, 4, and -1. Maybe I should do 8, which would just be C8. But we'll see. But to put that on the stack, we can say constant 4, constant 2, mul. That's 8. How about we call that C8? C2, C4, mul, and then return. So that puts 8 on the stack. So C8. We need a negative, which I thought I was going to make that an op for a long time, but that is C0 swap sub return. So let me demonstrate. We have the number 5. We say C0 to put a constant 0 on the front, which you can also do with 0. But like in assembly language, you have to say load byte 5. In the interpreter, you can just say 5. So 5 C0 load a constant 0. Swap them. Actually, can we do R to reset just the stack? No, like that, right? Yes, that resets just the stack. So we can say 5 C0. Okay, that's nice because now you can reset the stack, and that's cool. I haven't been really playing. I haven't had this in an interactive environment before, so it's kind of neat. You can just play with the stack this way. All right, so put 5 and C0 on the stack, which is just 0. I'm copying this line right here. So we want to swap them, and then run subtract. So that gives you -5. So that is why that is the definition of negate. But here, the much easier way, which I don't know why I didn't think of, you don't need this constant 8 because you can just say load byte 8. Right. Duh. In fact, you can load -8 like this. Load sign -8. Although I don't know if that works in this assembler. Let's see if it does. Let's just clear everything. 100, and just put a -8 in there. F8. Okay. Like -1 is right. it's FF, but there's a thing. So -8 is F8. Okay, so you can do that, and then we can say from, it's not 100, it's one hextrid, right? This is 256. We say read byte, and that should give us yeah, right. But 100 read signed byte should give us -1, -8, because that's what F is. Okay, so load sign should also give us -8. Oh, so we have to test whether this works. So load sign -8 return, and let's just call this like F. That was a display bug with this line editor I'm using. All these extra T's. All right, so now if I call F, it should run that and put another -8 on the stack. And did. Okay, so that worked. Just testing. I hadn't tested that yet. Actually, I think I did test it. I wrote a test case for it. Hello, person watching. Welcome. All right, so load a short or load signed -8, and then we shift, and that's all we have to do to shift it over. And then we have to mask it. How am I going to do this? We have to mask it, and so again, I'm just going to fall through to the low, right? Fall through. Falls through. And then we say NX. So NX returns bits 8 through, or 0 through 7 of N. I always say 8 through F. 8 through F of N. All right. So we should be able to load that again. That says clear everything, assemble this file, and call the clear screen function. There we go. And then I don't even know if I need the clear screen part. What? Too many defs? Oh, so this C is not clearing the dictionary, so that's a bug, and I'm just going to leave that as a bug right now. But I'm gonna put that as a bug in here to do like after this tomorrow. So C does not clear dictionary, leading to causing too many deaths. All right. But in the meantime, we'll just restart, and we can just do that. And then, so that assemble that file. The %C was unnecessary. That just cleared everything, but obviously didn't clear the dictionary of labels that we have assigned. And what do I want to do now? I wanted to say so like 4433 high, and that should give me 44. Yes, and if I say 4433 low, that should give me 33. It does. All right, so these two work, and then now we can just say that this is the low and this is the high. What is all this nonsense? So this says load byte dupe. Oh yeah, I was just in the middle of trying to find another way to write that, because I forgot that you could just put a -8 in there. Okay. So I'm going to keep doing this until it crashes. What happened? We have the numbers B and E here. Where are they coming from? They're coming because right here we have all these things and only the number F8. No. This right here, this bang B, which is something having to do with the address of cur, I think. If that's the case, there should be two of them, B and E. That's what they are. These are opcodes. Oh, these are the addresses of high and low. Anyway, so the terminal is still looking at this area of memory, so we need to update it to look at TMB. And I'm just, it should do this dynamically. But instead, what I'm going to do is, for now, I'm just going to go into the source code, and the Pascal source code of this program over here, which is called B4IX at the moment. I'm thinking about changing it to B4TM for terminal. And I just have to find the constant where I define where that screen starts. So we say draw term. Yeah, and I have a constant here that says where the address is. And it's 140. No, it's not 140. It's, I think I was trying to come up with a way to say this. So like 1 hextrid 4x0. I don't know. Say it's hex. I think it's just hex 140 is fine. But this should now be at 400. And now I have to recompile this, which is very fast. In fact, I think this recompiles it. We'll see. Yeah. So if I say 400, oh, now I can jump in front of it. Previously, I wasn't able to move the cursor before the start. So if I just put like an X there and then write a byte, that should write that to the terminal. Yeah. Okay. So that was all we needed to do to make that change. We have cursor X and cursor Y. So right now the cursor should be at 4. So this should be, the Y should be 4, and then the hex and the X should be 16, which is 10. So we'll say cur X. We should expect to get 16. Yes, and we say cur Y, and we would expect to get 4. Again, from these two numbers right here. And that works, so let's go back to the plan and mark those as done. Okay. So now you can see that we how do you write to that? Let's find out. I'm going to switch these and do emit next. We have everything to do to put this exactly there. So we have, all right, so we have, we can look at our definitions, right? You need like 1 extra pixel, 1 extra character. Maybe something. Why is it putting those extra new lines in there? I'm thinking the screen is too narrow. Oops. Oh, maybe it's just got an extra new line in there. I'm not sure what that's about. Okay, well, whatever. I'm gonna move this back. I will not worry about that right now. This is just showing all the places that we've defined. All the labels that we've defined. Obviously, it shouldn't have all these spaces in between, but these are addresses. So this is like the dictionary of all the definitions in the assembler. So print labels basically is what that command means. Coming up on an hour. I was expecting this to take about half an hour, so I don't know if that's going to happen or not. Probably would have taken half an hour to do it, but talking it through takes a little more time. Okay, so anyway, the terminal buffer is where we want to start. So if I want to put an X at the start of the terminal buffer, that's easy. It's just at TMB. And we say what it is, then we say the address, and then we write it. So write byte. There's the A. That's easy. And again, that's just writing to memory, and this is just viewing a piece of memory. The top part is just viewing a piece of memory as characters, as opposed to as opcodes or whatever. All right, so now if we want to move it, so we can clear that by putting a space. And if we want to move it over one, we can add the number we want to put in. So we want to put it at space, so it's 64 across. If we want to put it halfway through, I guess that would be at 31, which is 19 in hex. And we add that. So if we put an X there, I would expect that to appear right about here. A little off. Right, maybe we want 20 there. 20. Ooh! Oh, because oh, I understand. Okay. You don't when you have a 0 and you subtract 1, you don't get 9, you get F. There's one F. There you go. That's the halfway point. Right. That's the halfway point right there. I find that a little hard to believe, but if I say, wait, is that true? 16 is 64 across, so if I say 3F, that should be the very last column. It is. If I say 10, that should be 16. So no, 10. So F would be 16, and then 1F should be halfway, yeah. And then 2F should be another way, fourth way. That should divide it evenly into fourths. So it's just a little bit off from my point of view. I don't know, for whatever reason, that just looks like not the center, probably because of this space here, this blue space here. But that's the center. Okay. So the point of it is we add a number, right? And I was just confusing myself. So we add 1F. That's the halfway mark. We can type clear screen to clear all that. There we go. So now if we want to move it down one, we have to move it by the width. So if we say PM width, add the halfway, boom. Yeah, that does that. I'll put a X, something like that. Okay, and then the question is why? How far down do we want to go? And that would be for Y. And we're going to multiply it. Oh, sorry, ML. And instead of 1F add, we're going to say cur X add. Cur X and cur Y are not variables, so I can't use the @ sign for them. I have to use, I just have to call them as functions. They're functions, not variables. Very easy to make a mistake like that in these fourth-like languages and assembly languages and stuff. There's no typing, there's no anything like that. Like typing as in like, you know, type checking. But I believe this should work. Yes. So, right, so that said, here's the character we want to put. Find the terminal buffer, find the current Y position, multiply it by the width of the terminal to find the vertical position, add the X position, yeah, we have to do two adds. We have to add the width and then add the height as well. So it starts out here, that's the terminal, that's the position of the terminal buffer. Every line we add the Y, you know, so we add the width every time to move down, and then we move out. And so that's it. This is the code. And so emit is this. We're not going to take the character. We're going to take all this stuff, boom, and return. And so let's see. We'll start with the terminal buffer. I'm just thinking of how to format it. Yeah, something like that. I don't know. Yeah, that's about right. Emit. So this takes nothing on the stack and takes the returns the Y. This takes nothing on the stack, returns the X. Cursor position. Cursor Y position. Cursor X position. And I'm going to take these little utility functions and move them up out of here. And this will all be part of the BIOS. And then, so this takes a character and returns nothing, but emits character at current position. Okay. Okay, so we can load that. And now we can say like, you know, X emit. Ooh, crash. I don't know why it crashed. I'm not worried about it. Like, it shouldn't have crashed. I think I just had something corrupted in memory. I don't ask me. All right, so we put A there. So now we need to move the cursor. I was trying to think if I can reuse this cursor value, but because essentially we want to add one to the cursor now. Right, because every time you emit, you should move one. So if we say Oh, we can say cur c1 add and then write it back to the cursor. And that'll work for until we get to the end of the line. So let's load this again. You can see it's like appending each time. No. Oh no, it's appending because okay. Sorry. It's appending because I made the thing longer. Yeah, I made the code longer, so there's more code to compile. All right, anyway, so now if I say x emit, and then I say y emit, ooh, it didn't move. Why not? So we say cur x is 16 where it was, and then we say x emit, and cur x is still 10. Why? Oh, wait, what? So, okay, load this address, read the integer, load the address, and write the integer. Oh, because the return is here. Okay. Now if we say x emit, yeah, now it fills up the terminal. Okay, so we could also implement clear screen like this. We could say, so CS2 would be load the term with, oh, hang on, stop. We need this go to XY first. We got to reset the term. Oh, I guess we could. I guess CS2 we could say just set the cursor to 0. So C0, write the cursor. That clears all the bytes. We'll set A to 0. No, we don't need an A because the cursor is the buffer now. Is the loop variable now. So then we can say fetch the term width and the term height. Multiply them together, and then that many times we're going to say load byte A, let's load byte dot, and then call emit, next, return. Okay. Now if we call that, that should fill the screen. It's a for loop, right? It's going to fill the entire screen with the letter, with a dot. Or not. And just quit start over. In fact, I can, instead of loading that every time, we can say on the command line to assemble this file. BIOS term.b4a. And then we just can, now we have all that loaded. CS2, why didn't that fill up the whole screen? 400. So if I wrote, so go 00 it would be byte 0 or just constant 0, and then write to the cursor, return. So we say go 00. Ooh, something changed right here, which is the cursor, right? Okay. So if we say, yeah, so if we say like AA or AABBCCDD and write the cursor, you can see the cursor is stored in memory right there. So go 00, we'll clear it. And then this loop should fill the screen with terminal width, terminal height, and that many loops. So this is go 00. And then CS2. Why does it only go halfway? Is it? That's 64 by 16. Am I crazy? Of course it's 6. 40. 10. Four zero 10 multiply, we get 400. 16 times 64. 400. Is there a bug here? 400. And the cursor has moved, so it incremented. Oh, I know what's happening. It's because we're only taking the low byte, so I'm treating the cursor as if it's only the X position. So right, this is the encoding issue. So it only works until we've done 256 of these. So 8 times 64. So 8 times 64 multiplied should be 100. 200. Oh, I see. That's why it's 7 lines. Because when you subtract 1, oops. C1 sub is 1FF. Does that make sense? Okay, 1 2, 3, 4, 5, 6, 7. 407 mole. I don't know why this is doing this. Like, I know why it's stopping. It's stopping because as soon as the x gets to FF, it should stop. Oh, I see. Do I see? Yes, I see. That's cool. That's funny. Oh, that's funny. It's okay. So as soon as it does 256 of these, so 64. So as soon as it does 4 lines, then the Y position rolls over, and so now it's going 1 line down and writing another 256. So it's doing this line, and it's wrapping that line 4 times, and then when it hits the end of that, it moves down to the second line and wraps that line 4 times. Yeah, and somehow that winds up at filling up exactly 7 lines. All right. So anyway, what it should do, we have to do a little bit more thinking about this. So let's call it wrap. Wrap. That corrects. No, don't do correct. So correct. So we fetch the current x. And then we're going to duplicate that because we're going to need 2 copies of it. We're going to need a copy of it. So then term width. Got to fetch the width of the terminal. All right, so right now correct, right, is 0. Okay. But if we say at cur C1 add cur, right, then we say cur x, and that should be 1. 1 right here. Okay, so we can set the x position directly by saying we can load the address of, we can just say, put FF there. Cur x. No. Cur. Sorry. Cur. Quote it so we get that address and then write the byte there. All right, so now see that change to that. So cur x should now be FF. We can't do that with the Y position. To write the Y position, oh well. For that, we would say FF. To go back to to line 1, we would say cur C1 add and write the byte. And I will change this Control D. Again, I'm stack juggling in my head. It's hard to do this. So what we want to do is we want to start with X and Y. I'm imagining writing the go XY. So go XY takes an X and a Y. I don't have inline comments right now. Probably in fourth you would write like this, X, Y, and then that would end the comment. And then so we want to return what? Nothing, right? But we have X and Y on the stack, so we're just gonna imagine we have X and Y. Or I can use a comment at the end of it. Okay, so we want to set this, so we need to get the address of the cursor. Which is this, her. So now we have X, Y, and the cursor. We want to swap those and say over, which is just the same as over. Is it? No. Swap and then over, swaps these two, and then copies the C. Yes, this is what we want. Over. And now we want to add 1 to the second address so we can write the Y position. C1 add, that's C1. And then we write the byte, so this goes away. And we write the byte again, so this goes away. And we're left with nothing. This is go XY. Oh, I was going to do it to see if Gemini could do all this stuff, wasn't I? That was the whole point of this. Oh, well, I'm playing with my toys. So this needs to be, since it's actually, oh, that's interesting. Swap over. So this does, X, Y. Let's see if that works. And again, this is just messed up. Did I write it? I don't think I wrote that in the note. So this is a bug. And then this is a bug. Bug. Line editor seems sometimes shows stray characters after pressing enter. After input. After submit. Okay. So we'll ask Gemini for some thoughts on all this stuff in a minute. But first, let's do 5 go XY enter. All right, let's ask cursor to find a bug. So if I say 0, 0, go XY, I would expect, because we put the, let's actually set the cursor to like AABB. Or what we'll do 0, 0, 0, and then we'll just do CR so we can see the cursor. Or we can point at it with an arrow. Okay. Those bytes are ignored. So there should be right. It's these two right here. What can we do? We can do. We don't have an arrow we can draw, but we can do these symbols. Oops. Because those are registers. Yeah. So this is the cursor right here. These two things are the cursor. So if I say 5, 5, 5, 7, 5, 8, whatever, go XY. It did put something. 1, 2, go XY, I should say AB. That looks like it's working. So then what's wrong? Now at 1, oh, we really want 2, comma Y, don't we? Yeah, whatever. So it should put something right here, but I don't think it's going to do that. X emit. Is emit missing a return? No. Oh, wrap is missing a return. Right. Okay. So there's nothing to debug. Let's have the cursor implement wrap, or Gemini implement wrap. Wrap cursor at line in. All right. So that we've actually got quite a bit of context here for the for Gemini to work with. Let's see if he can do if it can do something. All right. So I'm going to add. So first of all, what do I change? Pass before ix.pass. So before ix, move hard coded screen to give more room. Buff, more room, and then the term B is what it's called, the TMB. TMB address, give more room, and amend that. Git log, and then git add BIOS term.v4a. We can go ahead and commit these. Git commit start on term, say term.v4a, or a, start on term BIOS. Start of mem mapped BIOS. Okay. So now we're going to ask Gemini to implement that. So let's go over to the BIOS. That'd be for it. Not the BIOS. BIOS.term.v4. Okay. So Gemini already knows something about the system here because you give it a Gemini, markdown, and so these are basically notes that it's taken of itself. But I pointed it at like the documentation, like all the opcodes and so forth. And by the way, this is all online at GitHub. get origin and get remote. Tangent storm b4. I could have just said that, shouldn't I? All right, so first of all, let me just make sure that let me fix this. So I believe that since I commented that out, we won't have this problem again, and we can do the same thing again. So we can say 1, 2, go xy, x emit, and then we say 1, 3, go xy, x emit, just put right underneath. Yeah, good. So this works, except it's going to have issues with wrapping. So let us now ask Gemini to do this. So since it knows about this, it knows how to use the debugger and all that stuff, but I don't think it will. Let's just ask it to fill in the thing. So for BIOS term. So say term tab is a start on an in or on a memory mapped terminal device for B4 virtual machine. I have implemented some basic commands to clear the screen and emit a character, control the cursor and emit a character. Position the cursor and emit a character. But I need you. What's missing? However, right now, when we emit the last character on line, the cursor winds up, cursor has an invalid state. Can you please implement the wrap word to properly update the Y position and reset the X position when the cursor wraps. For now, at the very bottom, if it hits the bottom, it can just the bottom right. If it crosses the bottom right, it can just loop back to the upper left corner. All right, that's quite a prompt. So let's see what it says. We're just going to let it think. I have no idea what it's going to come up with. What I've seen it do in the past, especially before I gave it the documentation, was to just kind of hallucinate what it thinks the syntax is. But now it's working in a file where, you know, where we've got examples of the syntax. You can see it working. It has the docs. So hopefully it's going to be able to reason this out and put it together. A lot of people tell me that people who don't use these LLMs and these, you know, agentic coding say, well, it's only regurgitating stuff that it's seen before. But like, this is a language it's never seen before. I'm still making it up. I'm still changing it every day when I work on it. So it doesn't have this in its memory, you know. So it may be translating, you know, other screen routines and so forth. What it's saying, but you know, but it's not. It's not just regurgitating completely from scratch. It's synthesizing something. Okay, so it says, of course, I'll implement the wrap word in BIOS term before A to handle cursor wrapping correctly. Here is the plan. I will replace the placeholder wrap with a new implementation. Okay, so let's solve it. It's there. The new wrap word will check if the cursor's X position is beyond the terminal width. That's what I want it to do. If it is, it will reset the X position to 0 and increment the Y position. It will also handle wrapping the Y position back to 0 if it goes beyond the terminal height. Here's the code I will use to update the file. Okay, and then we can press Control S to see the 15 lines that are hidden. Oops. I'm still using Tmux to scroll here, so I have to, there we go. So Control S causes it to redraw the screen, and then go back to Tmux and come back up here. All right, so what's it gonna do? See, no. So it didn't get it's hallucinating the syntax. Okay. So, well, that's not quite B4 assembly language. Please look at B4I test to see how the structured programming macros work, and note that especially for if then else. Oh, actually, that's not how it works. It's if T for if else then, because this is a reverse Polish notation. You put the condition, then you say if, then you say the then part, or the if so part. Really, .I is like if so, else, and then is like you continue. How about if so, else then? And also note, only comparison op is ops are eq and lt, but you have to swap and nt for not, for bitwise not. All right, so let's give it that information. So what do you think? What do we think this should look like? Really, it's a test on the cur x. So we fetch the cursor, we look at cur x. If it's greater than or equal to the terminal width, really if it's equal to the terminal width. If it's not less than the terminal width, then we subtract the terminal width, take whatever's left, and put the and we add that to the next byte. And then we kind of look at it again. So really what we could do is we could say, I guess subtract. You're kind of doing the same thing. You're doing a bounds check on a byte, and then you're moving to the next byte and doing another bounds check. So really there could be a word there that could be factored out. So maybe that would be how I would implement it. I don't know, let's see, we'll try and race it. So I'm gonna Emacs, I'll just make a new. So let's just talk about how I would do this. So we would say wrap, oh, that's weird. Wrap example, and we'll watch it doing its thing over here. Control, what does that mean? I must have pressed the key or something. All right, so it's doing something. All right, so before I look at 27 lines, that's a lot. So let's see what we can do. The fact that it's 27 lines means it's probably doing like a comment on every line, or it's rewriting something. That happens sometimes. It like wipes out, like unformats something or something like that. Let's see. Let's just think what we think it should be. So wrap cursor wrap example. So first, let's make a little word that says like cut, or what's the word? Like excess, like excess, right? So how about trim or clip? Clip is a good word. So we'll say X, or so we'll say N, and then the M, and so clip N to M, returning excess to max M. So clip would be something like, right, returning the excess. So we want both of these things. Oboe will duplicate the two things because it says N, right? So let's again write the stack. We have NM, and we over, which is N, and then M. So now the stack looks like that. And why did I do that? So is N M less than? So we say less than if it is, if. So that's our question. So these go away, and we have, less than, or is it less than? If so, zap, put a constant 0, and like that's it. If it's not, so else, the excess being 0, no excess. So we can really just return here, but we'll do it in the structured way and say then return. Else, we'll swap them and subtract. Okay. So that's clip. And now we say wrap. This is wrapping the cursor. Wrap terminal cursor. So what do we do? We say curX term width clip. We're going to duplicate that. And we say if that number is 0, or if that number is non-zero, hit the current X, swap it with that subtract it. So we're saying subtract the thing. And then we're going to write that byte back to the cursor. Write byte. That writes the X position. Like the dot I, the if consumes the flag here, so that's why. Wait, no, this is not right. Hang on, I did that completely wrong, didn't I? All right, so we have the excess. Hang on, let's do this. So we have nothing on the stack. So now we have X, Y, and the width. Then we call clip. Sorry, no. We just have the X and the width, and we have the clip. And then when we call clip, that produce. So then after that we get you know, the excess. The excess. But it's not, it's X and width. So the X and the width, and we get the excess. So now we call dupe, and that gives us 2 copies of the excess. E, so we start with the E on the stack, we have 2 copies of E. And we say if, that wipes out one of them. So, and then we know that E is greater than 0. And then down here we have E again, because we duplicated it. And E is E equals 0. E greater than 0. So E is greater than 0. There's nothing to do in this case. There's no else clause, it's just then. Nothing to do. Except to zap it. So that would be the stack 0 and then back. That's the stack, nothing. And here, if we have that, so then what we want to do, we have the excess. Okay, so so we have E. We want to put the cursor position on the stack. The address of the cursor position. So the address of the cursor, load I cursor. We're going to duplicate it. So C. Okay, so we had 2 cursors, 2 copies of the cursor, right? But we don't want to do that. We want to say swap and then over. So we have E cursor. We're going to swap them and then over. So that gives us that. We're going to add 1 to the address, the cursor address. C1 add. So now we've added 1 to it, so I'll call it capital C. That's the Y position, so we'll call it like X and Y. Cursor X, cursor Y. So the Y position, what we're going to do is we're going to add the excess to it. But it's an address, so we have to say duplicate read byte. So this is the actual Y now. We did that, we read the byte, now we get the Y. Wait. Hang on. C1 add gives us the Y, but what we need to do is we need to read from this, get Y, and then we need to write to it to put the Y, but we have to use a byte. So we need to say at Y and then write to Y. So let's actually call this like inc A, like inc B, inc byte at address. So we'll say by X. So say XA, and then we're going to consume both of those. So what we want to do is duplicate A, so that gives us AA, or XAA. And we're going to read the byte, that gives us the byte. We're going to swap. We're going to push this to the data stack, the control stack. We're going to add these two together, so that gives us the new value. We're going to pop it from the stack, so control to data gives us that, and then we're going to write the byte, and then return. Messy. But what are you going to do? That's how it works. Okay, and so then we would call all right, so now we would say load cursor and all this stuff that I was doing before. We're going to inc B, right? So load cursor, C1 add. So maybe like the Y address or whatever. That's this. Return. I should really make more space for these, for the code, right? That's interesting. Fetch address of y byte. Which really, this could be the right. So this implementation fetches all four and then shifts it around a bit, but really we could just fetch a byte. So this is another way to do it. And maybe we would. Oh, excuse me. So that's the y address, and then we're going to increment it by the value in e. That's it. Add excess to y. And then now we say the same thing, really, for the y. Cur y, ooh, I don't know what I just did. Cur y, tmh, clip. So that gives me the y and the height, the excess. And then do if so. I'm just going to say if it's off the screen, rather than trying like, whatever, we're just going to set it to 0. We got to reset x. So which would just be li cur. That's the address of the cursor. C0 right byte. And that's reset x. 0. Yeah, definitely. I need to put these at like at least 32 or something. I don't know. I always have this problem. I put it close and then, I get some longer lines and whatever. Should really look like this, I think. And like pick a specific line to always put at. 32 is good because, it gives us kind of half and half if your screen is 64 characters wide. Not that most are, but, the terminal we're making is 64 characters wide. So if we put an editor for source code in there, then I don't want to have a convention where it's half the screen is comments and half whatever. Okay. Right byte. And this is C0. And then return. Set y to 0. Zap and then return. Okay, so that's what I would expect it to be. That's kind of like, that's my implementation. I think that's going to work. But let's see what it came up with. So first of all, I think it's going to corrupt this file. No? Okay. Mm-hmm. I'm just going to add it to get so it's in the cache, and in case it decides to mess with this file. All right, so let's actually zoom in on the Gemini code here. Wow. So first of all, it did it all in one function. If x is less than the width. Oh, okay. So it's actually using the right syntax now. Let's see what it did. If x is less than the width for x, that does what it says. If so, do nothing. Right? Else, you could put a not there. X is greater than width or equal to width, in which case x is 0. New y oh yeah, so you only want to add 1 to y. Whereas I added the excess, which is wrong. I made a mistake. Didn't I? No, we only want to add 1 to y. In which case we don't need this. And we don't need this. And we just say inc b. We just add by 1. How about we say add? We'll call this add byte. Save it for later. I don't think we need it, but let's try inc b instead. Inc b inc by x. Let's say inc byte at a by 1. So that would be a and then nothing. So we're going to say dupe read byte c1 add swap write byte return. Which is obviously shorter and nice. Okay. Alright, so now we just add 1 to y, which is what I said. Inc byte. Reset x to 0. This was backwards. And since I didn't need that, we don't need the zap, and we can just say then. And really, we don't need clip because we really just need less than. Less than not, right? If it's not less than, which means greater than or equal to. And if so, and return. Yeah, we don't need the else condition. We don't need this. I don't really know how you indent those. I don't have a good style for that. Anyway, that's it. So let's see what it said. Oh, and it just leaves them on the stack. I actually like this implementation better than mine. Except I would use not for the else here. And then what is this doing down here? Instead of return, it says wrap return. I like this. I think this did really well. I'm impressed. Like it took it a couple of shots, but like that's the right way to do it. All right, so let's see if it works. Right, we'll give it a shot. Yes, allow once. Yeah, it ran the test. See, it doesn't know that tests have nothing to do with that. It doesn't have that kind of common sense. All right, so let's try it now. Let's go back here. Load that code. Oh, unknown word go xy. Just move them up here. Okay. So let's go to, so we'll go to 2. No, we'll go to, so in hex it's 40 across, so it's 3F. 2, go XY. Well, let's do 3 E2 go XY. And then we'll say like X emit, Y emit, and now the well, if I say I have a command that gives me both of them. Oh no, but I can just say cur x, cur y will put the coordinates on the stack. 0, 3. Oh, it's already wrapped. So it was on line 2. It worked. It's already way over here. And then we say z emit, and it's over there. Yeah, and it's on the next line. Hard for me to tell that they lined up. So it worked. So I'm going to call this G wrap G. Do I even call clip? I don't. I don't call add B. See, I made a lot of code that I didn't need to make. Okay, and Y adder. So I do have those tools. So these all work. Let's see if mine works. We're doing a competition here. Right, so this is mine. So I can cut it out later. And now I'll try the same thing. Oh, I have it all in the history set. So that's why. You say X emit, Y emit, and Z emit. It worked. Okay. So this stuff is completely unnecessary though, because like ChatGPT or what model, Gemini made better use of the things that were already there. So let's just copy this and write it the way I would write it. So we'll call this version wrap M, Michael's version, and then we'll do the final version here, which I think is this one. Wrap cursor is, yes, that's a good doc string. It indented well, okay. So we're gonna say not. What is this F? Oh, it's a flag, right. So a flag is the greater or equal to width. That's J notation. If so, then we set new x to 0. If so, x is 0. Y plus equals 1. And it's also only doing this. See, I do both of them. Like this check is unnecessary because this one's wrapped in an if. Then we can say, well, only check the y coordinate if the x coordinate wrapped. Because then otherwise, now check y. So y greater than equals height. So now we have 0 y f, and if so, y equals 0. So yeah, zap c0 if so, y equals 0, 2, and then but then at the end, and now update cursor with new xy, and then return. So almost verbatim. I took their version almost verbatim, except adding the knots, right? X equals 0, y plus equals 1. I'm going to put that all in one line. So y prime, and then yeah, I like that. So it got there in a much more straightforward way than I did. I like it. Okay, let's test this version too. I haven't tested the bottom. Let's do it. X emit, Y emit, Z emit. And so now let's go 3 F, and the last number would be F, right? Go XY. And we'll put another X in the corner. X emit, that should be bottom right corner. And now when we say A, that should go to the upper left. And it did. Okay. All right, so I will use this version and switch over to this GS. Git restore staged BIOS wrap, that'd be for A. I might stick these in a gist or something so that you can see the different version. It doesn't matter. All right. Git diff BIOS term.b4a. Term b4a. Go xy. Wrap. Cursor. No, go xy was already there. Add cursor wrap. Emit. Okay. All right, so let's go back to the plan. We have emit, we have go xy, Max X, max Y, do I really need this? Just subtract 1. If I need it, I can add it later. Not really important. Oh, space and NL, those are easy. I mean, these are all easy. Let's just do them real quick. Scroll up and down, that's interesting. Clear end of line. That's works on what we already have. And then adder. So that's an interesting thing. So these things are, oh. These ones are interesting. And we should also have like a to do write, or how do you say echo, write a string. So these are a little more interesting stuff. I was just in my mind, I was imagining how to put a string into the. Like, how do you put a string into the system? Because what you want to do, you can't put a string on the stack because there's no pointers. I mean, there are pointers, but you have to put a pointer to something. So what you want it to do is you want to have a macro that says, so it starts with a dot, and then anything in here, like it'll read up to the end of the quote. So this is actually an assembler thing. This is all Pascal code. And what it would do is put that into memory and then return the address of it. And it would also put a counter at the start that said how big it is. And I think that you would do 2 macros here. Because sometimes, like, let me show you the actual BIOS. Or even. So you see how it says, like, every time I define something, this is the assembler definition, but then like this is the definition in memory. Because like right now, only the assembler knows like the address of these labels and stuff. The actual machine cannot see that. It's like external to the machine. And so this is a way of putting strings into the machine itself. And what they are is, so this right here is a macro that makes a linked list. So every time we have one of these, you see they're pointing at each other. So we have find, and then that points to dec, and that points to inc, and that points to ext, and ename, entry execution token, and so on. And these are chained backwards. So it's a linked list, so you can find a word, and the machine itself can look it up. So it has to be able to have those names, and it has to be able to compare strings, and that's all implemented in here. But you'll see that in order to compare a string, you have to know how long the string is. In C, people often put like the C convention is to make strings as long as you want them to be, but when they end with a byte, it's a 0. It's kind of error prone and messy. Whereas these, the Pascal convention is to have a number that says like how long the string is, and then you can only read that many characters. So this says 3, and then there's 3 characters, and they're just laid out in memory. So what I'm proposing is that this could be replaced with this macro right here, and this would be a macro that would fill that code up like that. But if you're in the middle of a function, right, like if you're writing something and you want to say like, you know, print, so it's like hello, and then you want to say like hello world print, or I guess we're going to call it echo, return. So the idea is that this is just leaving a number in there. So so that's going to translate to, I'm going to just call it hi, right? Hi. So that's going to translate to O2H.I, because that's what the rule is. Because sometimes we just want strings in memory because we're doing data and we want to link them together, or just have a string somewhere in memory, right? We don't want it to do anything. But you can't just have that in the middle of the code. What you need instead. Okay, I'm in the middle of a video. I'll be done in a little while. Okay, I'll come down. I guess I need to go in a minute. So I'd have another macro that does this, or rather like this. And I think what this macro is going to do. This is called quote. So in the ASCII character set, you know, we have registers with these names. So we have these two registers, and then this one. You know, I use this one for the dictionary. This one is the last place that we've assembled. This one I haven't figured out a use for yet. But I think these two, at least for the macro syntax, I think what they're going to do, and really you don't have to be bound to a register. We can use parentheses or anything. In fact, I could implement this, or whatever. Any character can be a macro. But what I was thinking of, maybe we don't even need the dot here. But what this would do is this would code a jump over the string, over whatever you compiled in here, and then leave the address, and it would jump to this position. Yeah, you do want this to be a command. So it would be, I'm pretty sure that would be a macro on its own. And so it would jump to this position, and then this thing would go back and fill in the place to jump to. And then it would also load that position. Sorry. Yeah. This right here figures where the end is, and it tells the beginning to jump to the end. And then it also says, take the address from the beginning and load that. And so this would go into like, jump, or jump, or it could be a hop really. Hop is a short jump. Hop to end. And then this one would be, end. And then, say jump to end. You can't really do this, but jump to the end, and then here we define the end. You can't really do this at the moment. And then at the end we're going to say, so here's the beginning. Begin. So at the end of it we're going to say load the integer beginning. So we're going to load that address onto the stack, and then call, and then it says li echo call, and then return. So that's how this would decompile. Or it was how it would be assembled. And so this is a useful thing because this is also a function called a quotation. You could put any, you don't have to put a string in here. You could put anything in here. This would be a general mechanism that would be like, add, swap, mul, or whatever, That doesn't do anything. Admol would be the same thing. Right, but now you can pass this function to another function, right? You can do things with the quotes, but you can also use it to put this is wrong. Here, you want this address, right? So here you could load the function onto the. Sorry, what am I saying? You can load the function's address, or you could load the string's address. Either way. So then, rather than having to write h, rather than having to manually calculate the length of the string, you write hi. That's what I'm thinking that how strings are gonna work. How strings work outside in words, in words, outside words. Just hello, it's like the hello. Maybe something like that. I don't know. Maybe we need an escape syntax or something like that. Anyway, but I think that will be like this is already done. I've already implemented it for it, but it was calling a special opcode that actually it's in the files here. So put s, I think. Yeah, so write a string. So we have we store the s. We use s as a string pointer, as a character pointer. We stick. We grab the first character, which is the length. We read that, and then increment it. So we increment by 1. And we just keep doing that, keep adding by 1 and doing that, and then we call it e. So this is kind of nice. This is a function pointer. It's just one of those registers, but you can store the address of a function in the register, so that you can decide dynamically where to send the output. And so this will send all this output to wherever e is. So you would set like you would say emit bang e, and now e is a function pointer to emit. So we can say like x and call e, right? So if we yeah, we can compile this directly. So we can copy this over directly. So put s is let me make a copy of it and then put it all on one line so it's easy to type. All right, so this is just storing the S register, the old S register. Then we're going to keep doing this pattern of taking the constant one and adding it to it. And that also puts the current value of that pointer on the stack. So yeah, so we're doing it twice. one outside to get the length, and then that tells us how many times. All right, hang on. I don't know why I rewrote it again. It's actually much easier to read this way. But I want it all in one line, which is, you know, Forth-like code is very terse, and this assembly language is much the same. There you go, put S. Okay. And so now we need to assemble a string. So I've run out of, I can't scroll this yet. I don't have a scrolling thing for that. But I think I can say, I'll just put it somewhere in high memory. I'll put like 900. We will assemble the string. So I'll do just high for now. So two bytes, and then an H, and then an I, and there's nothing to return or anything because it's just data. Okay. And then we can look at that address. We can see that it's got 2 bytes. B is the second letter, so 2 HI. And we can say 900 put S, and it should say hi up there. Oops. So put S works. Except I'm not going to put that ugly way in doing that, and we'll do it like this. I think I'm going to call it put S instead of echo, because I have put N and so on. That so for numbers, I could call this put C, or whatever. Assign E to terminal, and we're going to put S, and we're going to have this be S. Assign to print string. Note that the address, see, it's using that address. It's using its own address. Like, it doesn't matter, because that's the nice thing about a stack. It restores it, and it's just fine. Okay. So if I load this, and we do that again. So we'll put HELLO. And a space. And that is HELLO, exclamation point space. That's 7 characters long. So we'll put a 7 there, and now we can say 900, and we can just say S. Oh. And then later, if we want to repoint that somewhere else, we can always call put S explicitly. Okay, so back to the plan. So we have put S. Right, so this is the other way of writing a string. So really, there's an implicit to do in here that to do is macros to write strings, but we don't need to do that right now. I'm putting that down here in the inbox here. where I've been keeping notes for all kinds of fun things that I might want to do later. Okay, so emit a space. That's easy. Space and NO. Actually, new line is not quite so easy because what do you do when you... so new line is cur y we want to go to xy, right? So we're going to set x to 0. Current y add c1 add, and then go xy, right? So that's new line. Return. So now if we say 900s new line 900s, yeah, so now it wraps to the next line. All right, so that's that. That's easy. Space is super easy. Space is really just a yeah, we don't really need space. It's just that this is awkward to write. The space with the quoted space is just a little awkward. Return. I should write hello with 2 spaces in between. Ooh. Underflow of DS. Oh, because I didn't put a load byte in here. So there's hello, and we do it again like the space, which is already compiled or assembled. I redefined it. Because when it crashed and I reloaded it. This should put, there we go. So you can see the different spaces. So that's easy. New line was a little hard. Max X, screen width -1. Okay. Do I need that? Max X is term width. At term width is at TMW, and then constant 1 subtract, return, and the same thing for max Y and H. So if we say TMW, TMH, that's the 40 and 10, so 64 by 16. And if we say max X, max Y, that should say 39 or 3F F. Yeah. So because they're 0 based, 0 index. All right, so those are easy. Clear to end of line. Okay. I think this is a good stopping point. Yeah. Because for all of these, they require a little bit of work. And I would want to compare what I'm doing to what Gemini comes up with. And do some more comparisons like that. But I'm getting actually pretty hungry. And other people are asking for food, and it's kind of bedtime. So I'm going to wrap this up. But I think we answered the question, like given some prompting, it is able to it's able to write code in the, maybe not exactly in my style, but it's writing code that is usable for this language that I'm making up. And yes, it is like Forth and it is like other languages, but this is my syntax, and I taught it my syntax with just a couple lines of feedback, and it worked pretty well. And it implemented some somewhat complex logic. It made a simpler implementation than I did. But whatever. I think that's a good thing. Because now, the more I treat it like this, we can give it things to do and test it and so on. All right, so thank you, Gemini, for your help. Thank you for everybody who watched this. I think I'm actually gonna edit this one, and put it up and just show what a session is like. Maybe just cut it down to just that one little section. But we'll see. And maybe I'll do this again sometime. I don't know. I'm not gonna promise to do it tomorrow. I've done streaming 2 days in a row and I haven't streamed in ages. So turns out if your computer is getting slow and unusable and your camera is not working, one thing you can do, which I learned from ChatGPT and Claude, is replace the thermal paste in your cooling system, because my CPU was throttling because it was overheating and causing all kinds of problems. And that's one reason I haven't been streaming. Another is that I've been working on private stuff for a startup that I am making, and I'm not quite ready to share that yet. So, although you've seen some of it if you've seen this channel before. Anyway, I'm done rambling. Thanks for watching, and I will see you again soon.